right, everyone, welcome back. With college basketball in the air, I figured with our third podcast of Unit 3, we would bring a special guest podcaster to talk about momentum. And that special guest podcaster is right here next to me. It's Dick Vitale from ESPN College Basketball. Welcome, Dick.
Whoa, baby, this is incredible. I'm doing a podcast, baby. I can't believe this. Oh, Ted, thank you. Thank you for having me here. And I want to talk to you guys about momentum, baby. It's momentum time. That's when a college basketball team has Uncle Mo on their side. And that other team, they got to take a timeout. They got to burn a timeout.
I'm sorry, Mr. Vitale. Thanks. I actually don't need you. You can fly back to Bristol now. We're just going to talk about the scientific type of momentum, and that is what we're going to try to do today. Sorry about that. So let's talk about let's just define what momentum is. Let's give you an example. Here's Hall of Fame pitcher for the Texas Rangers, Nolan Ryan, storied legend of baseball. He could throw a fastball well over 100 miles an hour, and he's the all-time leader in strikeouts with 5,173. I don't know, something close to that number. So, all-time leader in strikeouts. He's going to hurl a fastball towards this catcher's mitt. All right, and so the ball is in the air. Now he's going to release that ball, and once he releases it, he's no longer applying a force. That ball's traveling with a good velocity, and it's going to go thump into the catcher's mitt. And when it hits the catcher's mitt, it's also going to have a force. It's going to accelerate into that catcher's mitt, okay? Because it's obviously not going zero, but it's also going to slow down, and so there's a collision there. So one of the things that momentum deals with is projectiles, okay? And that baseball is a projectile, okay? And when that ball is in the air, it's actually not having a force applied to it. And actually, when the velocity when it leaves Mr. Ryan's hand to when it hits the mitt is actually slower because it's got all this air resistance. So if we just were to draw the forces, we have the force of gravity. We don't have a normal force. So there's no force holding it up. So it is falling. But we also have the force of the arm, which doesn't exist because he's no longer hitting it, but we also have the force of resistance. So this ball, which doesn't have any forces being applied to it at that point in time, it's just traveling. It's just in motion. Okay? That ball doesn't have force, but it does have momentum. And momentum is kind of how we would consider it to be this function, this property of a projectile. And we're going to say that it actually transfers the force or carries the force. So it takes the force from Nolan Ryan's arm and applies that force to the catcher, but he's not actually standing up there punching the catcher's mitt. He's throwing a projectile. Let's put an S there. Transfers force. So if you want to apply a force to something from far away, like I'm sitting here in 209 right now, and I want to shut the light switch off, I can pick up a ball and hurl it at the light switch, and perhaps I'll be able to apply the force to the light switch and shut the lights off. So it's for projectiles, and it can be for anything that's moving, but it has momentum. So the projectile is carrying the force from one location to the other. It's got momentum, but it doesn't have any force. And so to quantify that, we want to just come up with a formula here, and we're going to say the momentum is a product. Okay, it's a product of the mass of that projectile, and it's multiplied by the velocity. Which means if you have a larger object, it's going to have more momentum if the velocity stays the same. Or if you have the same object, but it is going faster, it's going to have the same, or it's going to have more momentum. We abbreviate this with a P. I don't know why it's a P, it's a P. P stands for momentum. So P equals mass times velocity. Or we can just write next to each other, mass velocity is equal to P. Okay? Now, the units for this are, well, we always multiply the units, so mass is going to be, let's put that back. Mass is going to be in kilograms. Velocity is going to be in meters per second. So our units for P are going to be kg times meters divided by seconds. It's almost a Newton, but we're not squaring it up here. And there's no real funny name for it, or like fancy name for it. It's just kilograms times meters divided by seconds. Momentum is a vector quantity. What that means is that because P equals equal to m times v, and we know that velocity is a vector quantity because it has direction, which means momentum always has some sort of direction to it. And that also means we can add momentums when they are in the same direction. Momentum is also a conserved quantity. Conserve means to save, and so after and before before a collision occurs, so we say this is P before, we're going to have a certain amount of momentum, but it's going to equal the same momentum after the collision. So regardless of what type of collision it is, when that projectile hits the catcher's mitt, there's the momentum that was there at the point of collision is going to stay there. It might dissipate as friction, or in the case of a catcher's mitt, you hear the mitt pop. You also can actually, it heats up a little bit, but these are all forms of energy that get saved in the process. Let's try a practice problem using the equation P equals m times v. A softball with a mass of 160 grams is traveling at 6.2 meters per second. What's its momentum? And that's P. Well, we have the mass. The mass is 160 grams. We have the velocity, 6.2 meters per second. But we do not have momentum yet because we have to convert grams to kilograms. So let's do that by multiplying 1 kilogram over 1,000 grams. And that will get us to our momentum. So that's going to, if you multiply those together and you cancel out the units, right there and right there, we're going to get 0.99, almost a full kilogram per meter, or times a meter per second. Let's talk about another practice problem, but this one is involving a collision. We have a small car, and that small car is driving on an icy highway, so we get to ignore friction. And it loses control and strikes another larger car. The small car has a mass of 1,800 kilograms. It's traveling at 6 meters per second. The second larger car has a mass of 2,400 kilograms. Okay, and so the question is, what was the velocity of the second car after the collision? Let's take our equation when we talked about conservation. So P before is equal to P after, and let's actually expand that a little bit so that we know that P is equal to mass times velocity. We can say mass before times velocity before is equal to the mass after multiplied by the velocity after. So when these two cars collide, all the momentum from the small car in the before section, so this is small, actually all that momentum gets transferred to the larger car after. Whoops. So we'll say larger. So if we set this equation up, we have 1,800 kilograms. This is mass before. And we have the velocity before at 6 meters per second. And that's going to equal, I'm going to make the other side green, and we have a larger car of 2,400 kilograms times velocity after. Our goal is to solve for velocity after. So what we can do is divide both sides by 2,400 kilograms. We have to cancel. We have to we have to make sure that we include the units there, because now we can cancel. We're left with meters per second, and if we do the math, before we do the math, we should probably get rid of these two as well. Well, we might as well cancel out these zeros, and we can cancel out the 6 and put a 4 here, because 6 goes into 24 4 times. We get 18 divided by 4, so that equals velocity after is equal to 6, or I'm sorry, let's erase that. It's 4.5. I'm getting there. 4.5 meters per second. So after that collision, that car of 2,400 kilograms was moving at a velocity of 4.5 meters per second. All right, I think that's enough. I want to thank Dick Vitale for coming in and putting in the effort. And I guess you're on break right now, so enjoy your time off. Do a little momentum and work on that packet. It'll be due coming up pretty soon. Good luck.